Welcome to this presentation on the ideal gas law. And we've been talking a lot about different kinds of gas laws which relate different kinds of variables, most namely pressure, volume, and temperature. But right now, I'm going to present to you an equation which is going to be incredibly useful in an incredible number of problems, and that is the ideal gas law. And the ideal gas law is right here. It's really just an equation. And before we derive it or talk about what it means, I'm just going to give you a really pragmatic overview of how to use it. So the ideal gas law says that pressure, if we take a gas, pressure times the volume of that gas is equal to the number of moles, so that N is the number of moles, N moles, times a constant R. That constant is known as the ideal gas constant. The ideal gas constant, times temperature, as always, in Kelvin. So a useful way to say it, to remember it, is PV is equal to nRT. PV is equal to nRT. Just say it a few times until you start to etch it into your brain. And so the way we use this equation is it's very similar to any other kind of equation in chemistry. We want to know some of the variables to find out some of the other variables. And so within this equation, we've got four different quantities. We've got pressure, volume, temperature, and moles. Remember, this R is a constant value. It's not a variable. And so whenever we know three of these quantities, we can find the other. And so a bunch of problems, both on the AP exam if you're planning on taking that, or on your next test, a bunch of problems are just going to give you three variables, three of these quantities, and ask you to find the fourth. And to do that, all you're going to need to do is manipulate the ideal gas law to isolate the variable which you're trying to find. So if we want to, for instance, if we were trying to find P given all the other variables, we could divide both sides by V to get P equals nRT over V. And you can do that. I am very confident that you can do that for any of these variables. A quick note on units. It is very important to consider which units you're given and which units the ideal gas law requires. Now, what really determines the units which are required to input into the ideal gas law is this R constant. And this R constant, the ideal gas constant, is equal to, I'll just write it over here, it'll always be given to you in problems, but I'll just write it over here, is equal to 0.082057 liters times atmospheres over Kelvin times mole. Now we can change the ideal gas constant to take on different variables, but when you're given the ideal gas constant with these variables and with this number, you need to make sure you're inputting all your other quantities with these different units. And so whenever we use 0.082057 as our R value, we need to make sure pressure is in atmospheres of pressure, volume is in liters, temperature is in Kelvin, and obviously moles is in moles. Now we can, as I said, we can find different values of R. In fact, you can go to the Wikipedia page for the gas constant and find tons of different values of R for different kinds of units. But whenever we're given this value, we need to make sure our pressure is not in pascals, it's in atmospheres. It's not in cubic meters, it's in liters, etc., etc. So that's just something to look out for in problems. You may be saying, oh my goodness, I'm never going to be able to remember this expression PV equals nRT, but I'll just share with you sort of the strange way I remember it. I have a friend named Peter Verhakey, and so I noticed that was PV, and so I made up a mnemonic that's Peter Verhakey, never really talks. Never really talks. Now this is completely untrue. I don't want you to get the idea that Peter cannot speak. He talks all the time. But it's a helpful way to remember the PV equals nRT. You've got Peter V, PV equals never really talks, nRT. Maybe if you're a soccer fan, you could remember Patrick Vieira, never really talks. But however you remember it, it's not too difficult to remember. You're going to want to memorize the ideal gas law. But you may be saying, where the heck does the ideal gas law come from? Well, we've looked at the combined gas law in previous videos, and so maybe we can use that as a jumping off point. We know that the combined gas law says something like this. P1 times V1 over T1 is equal to P2 times V2 over T2. Another way of stating the combined gas law is just saying that pressure times volume divided by temperature is equal to some constant value. So that when these change, we need to change some other variable in order to maintain that constant value. And if we write out the ideal gas law here, we can see that all we've done is if we isolate the constant on the right-hand side, as we've done here, we get PV over NT, so just divided by N times T, is equal to R. And so we've still got this constant value. We've still got this constant value. We've still got PV over T. Remember, we had PV over T equals constant over here. All we've done is introduced this mole value. Why have we done that? Well, we know that it's kind of intuitive, that if we add moles, if we increase moles, so we just add more gas to some system, we're probably going to increase the volume, because more of something is going to take up more space. And if we maintain a constant volume, well, we're probably going to increase the pressure, because more particles bouncing around inside a basketball, for instance, if we pump more air into a basketball, regardless of the temperature of that air, we're going to give it more pressure. There are going to be more collisions, there are going to be more particles hitting the outside of that basketball, and its pressure is going to be greater. So the ideal gas law, all it really does is it incorporates moles into the combined gas law and finds a constant which is independent of the identity of a gas. And so the ideal gas constant, R, is independent of gas. So you could be dealing with, argon gas, you could be dealing with helium gas. This R constant is not going to change based on the gas that you're using. An interesting sort of analysis that we can do on the ideal gas law to further this idea that identity is not important is to isolate, let's see, I'll choose a nice orange color, is to isolate V. So let's look at how V varies. We can see that V, so if we go up here, we're just going to divide both sides by P. V is equal to nRT over pressure. And so we can see that if we have a sample of gas, we want to find the volume, we don't need to know what kind of gas that is. Remember, as we said over here, whenever we're given these variables, pressure, volume, temperature, and the number of moles of a gas, we can always find the one that we're not given. It doesn't matter what that gas is. So, similarly here, if we know temperature and pressure, say those are constant, let me just circle those in green, say those are constant values, we see that V, R is also a constant, V is just going to vary with N. If we increase the number of moles, the volume is going to increase. And what's more, the volume of one gas with 1 mole of that gas is going to be equal to some completely different gas also with 1 mole. So again, identity is not important. And another way to state this, and this is the final thing we're going to do in this video, is using Avogadro's law. And Avogadro's law, again, may come up on your next test or on the AP. It's a really, really simple concept, and you can always use the ideal gas law in this form, in the V equals nRT over P form, to prove it. But all Avogadro's law says is that at any given pressure and temperature, equal moles of gases of any identity, so identity is unimportant, occupy equal volumes. And that makes sense. We see that if we know temperature and pressure, T and P, that if we have the same number of moles, well, this is just going to equal some number. And for any other gas, it's also going to equal the same number. And so it's going to equal the same volume. And an extension of this, and perhaps the most useful extension of Avogadro's law, is to say that at 0 degrees Celsius and 1 atmosphere of pressure, 1 mole of any kind of gas, any gas, I keep stressing this, but it's important, identity is not important, of any gas is equal to 22.4 liters. And this 0 degrees Celsius and 1 atmosphere of pressure is an important condition. This is called STP, or standard temperature and pressure. So whenever you're given a sample or a problem says, take some gas at STP, you should know that STP is just referring to 0 degrees Celsius and 1 atmosphere of pressure. At STP, the volume of any gas, or the molar gas, so the volume of 1 mole, molar volume, is equal to 22.4 liters. And so if I have, let's say, I don't know, 1.6 moles of gas, and I want to find the volume it takes up at STP, all I have to do is multiply this number by 22.4. 22.4 liters per mole. It's the molar volume. And if my calculations are correct, that's going to give you 35.8 liters. And so whenever you're given the moles of a gaseous substance, of a gaseous sample at STP, you can always figure out the volume of that sample regardless of identity using this 22.4 molar volume. And you'll memorize this number. I strongly recommend that you devote some time to memorizing it, because you can always use the 22.4 to figure out the volume of any gaseous substance at STP. So that's just a quick overview and some extensions of the ideal gas law. But just remember that whenever I spy pressure, volume, moles, or temperature, or any combination of those three in a problem, my brain should say, hey, I'm going to use the ideal gas law to solve this problem. Thank you very much, and I'll see you in the next video.